Hello, my name is Dylan Brenneis, and I'll be presenting this work on behalf of our larger study team listed here. Today, we'll discuss a preliminary investigation that starts to consider how people might interact with technology that actively learns while they're interacting with it, and how we can study those effects. As our technology has evolved over millennia, so have our interactions with it. Technology has traditionally been hand-engineered to produce reliable performance and, in turn, predictable human interaction. Even where modern learning systems have been employed, the system is typically pre-trained before deployment, and then its parameters are frozen and its behavior is fixed. Technology that dynamically and continually learns while it is being used has great potential, but comparatively little research has actually investigated how humans interact with these systems. Most research involving humans that interact with learning systems consider the case where technology learns something from or about the person interacting with it. Guangliang Li and colleagues provide a good summary of this work. However, this line of research focuses mainly on what the agent is able to learn, rather than actually on the nature of the interaction. So, additionally, system learning dynamics are inherently intertwined with the interaction dynamics. In Power to the People, Salima Amershi and her colleagues convincingly argue the case for separating human interaction from agent learning to study how people actually interact and want to interact with learning systems. And by focusing on the human side of the interaction, they're able to discover novel modes of interaction, unforeseen obstacles, unspoken assumptions about machine learners. And we agree with their emphasis on allowing for and studying natural human interaction with these systems, but we're particularly interested in how active learning on the agent side affects that interaction. Additionally, a meta-review of factors that affect trust in human-robot interactions suggests that the system-specific factors such as behavior, predictability, and failure rates greatly affect human trust in autonomous systems, which suggests that human interaction may be greatly affected by changing levels of agent competency over the course of learning. Our study specifically considers interaction with an agent that learns from scratch to predict the timing of an external event and communicates information about that prediction to a human user. The system learns to predict the event using a general value function and cues the human that the event is oncoming by way of Pavlovian signaling. In brief, the calculation of a general value function is a simple modification of the standard reinforcement learning method, where instead of using state values to predict upcoming reward, we use state values to predict the future value of some signal of interest. Imagine, for example, that you wish to predict the onset of a step function pulse. When properly learned, the prediction will rise ahead of the signal's onset and then go back down ahead of the signal termination. Pavlovian signaling now makes use of that prediction by sending some signal to the user at whenever the prediction is below the threshold value, and a different signal whenever the prediction is above. So I'll now describe the details of our particular experiment setup. We study the interaction in a virtual reality environment, which simulates a frosty hollow. The participant must stay in the center region in order to accumulate heat, while avoiding pulses of wind, which arrive at roughly 20-second intervals. If the participant doesn't duck out of the way before the wind comes, they lose the heat they've accumulated so far. The agent's prediction of the wind is communicated to the participant by vibrating their handheld controller. And once the participant has gained enough heat to fill their heat gauge, they can raise their controller above their head to cache their heat as a unit of game reward, which can't be lost to the wind. We test two different agents, which differ only in the way that they represent time. The first uses a bit cascade representation, which discretizes time into equal chunks and resets at the falling edge of each wind event. And this representation learns accurately, but requires several pulse periods for the predictions to rise above that threshold for signaling ahead of the pulse. The second agent uses a tile-coded trace representation, which discretizes time according to an exponential decay function, and also resets at the falling edge of each wind event. This representation is less accurate around the time of the hazard, but it allows the prediction to quickly rise above that threshold for signaling after only one or two instances of experiencing the wind period. In addition to varying the agent's representation, we varied the interstimulus interval, or ISI, the period of time between wind events. In the fixed condition, wind arrived at regular 20-second intervals. In the drifting condition, the ISI differed from the previous ISI by some random amount, up to 2 seconds, and we clipped the ISI within a range of 12 to 22 seconds. For the random condition, the ISI is sampled uniform randomly from the range of 12 to 22 seconds, independent of the previous ISI's duration. And in all cases, the wind pulse lasted for 4 seconds. Due to constraints imposed by COVID-19 pandemic, we conducted the pilot study with just a single expert participant who was a member of our study team. To avoid injecting biases, this participant was not involved in any of the quantitative analysis. Further, we stress that we do not claim that these results are generalizable to a broader population. But, as is the nature of a pilot study, we aim instead to discover general themes that will be worth careful investigation in a larger follow-up study. Our study followed the format of our approved Human Research Ethics Protocol. Our participant ran 9 trials per study session, 1 trial for each combination of ISI and agent type, including no agent. A total of 10 sessions were conducted, and our results are presented as the average values over the 10 sessions, and the appropriate pairwise statistical tests throughout show significance at the family-wise alpha is 0.05. So looking here at the number of time steps that the participant was hit by the hazard in each condition, we see that for the fixed ISI, the participant does better when paired with either agent as compared to none. And in the most challenging condition, where the ISI is changing randomly, the participant is hit the least when paired with the tile-coded trace agent. This plot shows how the participant's exit timing relates to the signal given by the agent for each pulse encountered over the course of the trial. So exit times below that dotted line indicate that the participant left the goal region before the agent sent the cue. So we see that in many cases, when paired with the bit cascade agent, the participant must be relying on their own internal timing to choose when to leave. When paired with the tile-coded trace agent, the participant leaves the goal region after the agent signal most of the time, leaving the possibility that they're using the agent signal as a cue to exit. However, when considering the qualitative analysis, we see that the interaction there is actually a little bit more complex. So we asked our participant to jot down a few qualitative notes about their experiences interacting with the agents while going through the study, which revealed some surprising components of the interaction. Note that while our participant had a deep understanding of the mechanics of learning agents of this type, they never knew which agent they were interacting with at any given time. And from these qualitative notes, we learned that they trusted the agent more when it learned faster, and that trust enabled this participant to modify their behavior strategically. We see this strategic behavior modification in the quantitative data as well, in events where the participant takes on unusual risks. The participant is paired with the tile-coded trace agent in 13 out of 14 instances where they actually race to beat the pulse by caching a point after the agent has warned that it's coming. So knowing that they're in a state of potential danger, they choose to stick around because they feel that they have enough time, knowing what the agent typically gives for a cue. Moving from this pilot study to a larger scale human interaction study with a greater and more diverse participant population, We call out a few aspects of particular importance. First, trust is a particularly important component of human interaction with learning machines, and direct measures of trust should be included to study this aspect. A simple modification to this study that might allow that would be to introduce a voluntary and cognitively demanding distractor task that would be performed while gathering heat. So engagement in this distractor task could be a measure of trust, since the participant would need to rely on the agent to count the interstimulus interval timing. Additionally, measures to assess how participant strategies change over time could help illuminate the effect of trust on strategic behavior. Finally, a pre-trained agent baseline would help to discriminate between the effects of online learning and the more general effects of just simply interacting with an agent. In conclusion, we identify trust as a major component of a person's interaction with actively learning technology, and that in turn can affect strategic behavior. A larger scale follow-up study should include specific measures of trust to determine how trust is affected by online learning. Thank you so much for joining my presentation. If you're interested in learning more about this and related studies, there is another paper that is being presented here at ALA with a similar author list. I encourage you to check it out. Thank you so much.